Just to remind you what the formal ADS is, it's given by this metric where tau is the modulus and coordinates, time coordinate is periodic with this 2 pi period, and the radial coordinate runs from 0 to infinity, and at infinite radial distance we find a conformal boundary, and this boundary has a topology of a torus, so the formal ADS is just a solid torus characterized by this modulus. And this torus is not general because the modulus is pure imaginary. It means precisely that if we realize the space, I mean, if you realize torus as a rectangle on a two-plane with identified edges, so in this case we have very particular rectangle without twists. Now this is my final slide, and first of all consider the case of zero-point conformal block. That is, we just switch off the external leg, and in this case the corresponding graph is given by a circle running around this dashed line which correspond to 0 radius, and the total action is in this case is given by two terms. The first term is the gravitational action evaluated on thermal ADS, and the second term is the circumference of the loop, which can be easily computed from that metric from the previous slide. So in this zero-point case we find this expression in terms of tau, and coming back to modular parameter, which is related with tau by this formula. Tau is just proportional to logarithm of q. So we see that this is the logarithmic contribution seen on the previous slides, and if we switch on the external leg, we also can show that more general duality holds, and in this case this arm has three terms including the length of the leg, and the correspondence, what is more important, holds in the so-called low temperature approximation. This is because we know that on the gravity side there are a lot of saddle points parameterized by different values of a modular parameter, and the formal ADS corresponds to infinite modular parameter, contrary, say, to ETZ black hole, which correspond to 0 modular parameter, and they are related by model transformation. Okay, so our claim is that the block length correspondence in this case is valid in the low temperature approximation, where the temperature is just the inverse modular parameter. So now let me summarize, and we consider it torus conformal blocks, and observed that there are 4 different types of semi-classical blocks, and we established a chain of connections between these different semi-classical blocks and explained the appearance, the appearance of semi-classical blocks from the Virasoro algebra perspective. Also, we holographically realized the one-point torus blocks and the corresponding geometry in the bulkage of the thermal ADS, and the correspondence holds, as I said before, in the low temperature regime. So there are also some open questions. Unfortunately, I have no time to do this time. Thank you very much.
For instance, for the torus, with one insertion you have N=2 with matter in the adjoint. This is the simplest example I can think of.
It's not N=2.
So the Grasso partition functions, if there is any via some Maggitti conjecture, I don't know.
No, the claim was that one-point torus blocks are related to 4-point sphere blocks. So there is a complicated map which relates these two functions. And in particular, it would be interesting to understand how.
No, I was referring to the fact that the conformal blocks or the correlation functions are related via some IGT conjecture, you may think, to the Nekrasov partition functions. So it's Seiberg-Witten theory, partition, but with the supergravity backgrounds.
You mean AGT duality?
Yes, AGT.
For us, it's just a calculational tool, actually. We suppose that we have some expression for conformal block, and this expression can be obtained in various ways. It can be done using Zemolodchikov recursive procedure. It can be obtained by using AGT combinatorial representation or monodromy method, but for us it really doesn't matter which way we used. We need a final expression for this function.
Modular bootstrap on the torus.
We have not seen it yet because we know that correlation function is modular invariant, but conformal blocks are not. So it would be interesting to check how these modular transformations of conformal blocks are reflected in the bulk. So how going between different saddle points of gravitational actions using this modular transformation is reflected with modular properties of conformal blocks. It's open question, actually.
We don't have any other question. Let's
Thank you very much.
Next would be about problems in SPT.
Of integrability, yes. So first of all, thank you the organizers for putting up this conference and for allowing me to talk here. My hope is definitely that I can actually use all this time at GGI to continue further this work, because there's just too many unknowns. So I'm just going to motivate all the work that we've been trying to do ever since. So this work is basically what's contained in the paper of already a year and a half ago. Well, we've tried many different things from then on. Unfortunately, there's more unknowns than actual full understanding. So the main idea is that, I didn't try this, so I am focusing on any other contributions other than just winding of particles, of massless particles m times, need to somehow cancel, because the shape is the same. So it's or they all contribute to cancel the factor of 2. This is not completely obvious, but it's not. But definitely there's some, meaning these contributions, just these contributions seem to already be of the correct shape. So I would like to finish with a set of we've tried, of course, many different checks and tweaks to what we were calculating to see first if we could determine the factor of 2 apart from actually determining the full TBA. So one of the things is that, for example, in terms of mismatches, circular strings in SU2 are not the only ones that have a mismatch. So we have the SU2 circular strings and we have the SL2 circular strings. So here we have that the K is basically a L over 2 J charge, so in S3. The SL2 K is S charge, so ADS, also L over 2. And in this case, if we do the same calculation, again, we get the correct order, but we do not get the correct coefficients. So it's not, meaning it's just a factor of 2 times the mismatch or anything of the type. Huh? No, in this case, even even each term doesn't match, the coefficients don't match. So we get the correct 1 over J cubed, 1 over J fifth. So it's the correct orders, but the coefficients actually are not the same. So we get K minus M to the cube time, meaning because here for the SL2 you have both K and in the winding M for the resolvent, and the coefficients definitely do not match. So also we need to make sure that we don't break the agreement that you can find for the SL2 short strings and also for the giant magnon. So it seems that meaning if you have very large multi-particle states that there's a mismatch, but if you don't have such a large state, there is agreement, and definitely meaning this needs to be taken into account. Somehow the massless particles do not cancel out their contribution. And of course there's all of the other terms that if you did the massless TBA and meaning if you had a massless massive TBA and you could actually, instead of doing an expansion of this log, actually do the whole calculation with the log, you would get all the massless contributions, and in that case the hope would be that you could actually determine the full difference between the string semi-classical calculation and the beta ansatz massive sector calculation. So that's basically it. So this formula is definitely a trial formula, even not meaning it's just a kind of trying to do a multi-particle state with an N winding. Of course, with the winding, meaning if you can see here, we didn't assume massless scattering, so that we would get kind of a -1 to the N if we did N winding and we considered the -1 to the N. In fact, for the calculation of the circular strings, it doesn't contribute because the odd terms actually are 0 in the calculation, so it doesn't make a difference. But once again, that formula is just, how do you say, protocol?
Is at the same value for the ground state, but then for the smaller values, the black holes will dominate, and for bigger values, the ADS ground state will dominate. So this is again a Huygens-Page transition.
in 2+1 dimensions. Okay, so what we shall do here is to do exactly as I just said. These are very old results, but in the case of highest spin black holes. So that means I will work in 2+1 dimensions, which is a theory where you can couple highest spin charges in a very easy way. And then consider the same problem. I will have a partition function given by a set of n-1 charges, Q2, Q3, Qn, with their corresponding chemical potentials. Mu2 and Q2, you can think of them as like the first one would be like the temperature and the mass, and then all the other ones are the highest spin charges. So mu3 to mu-n are fixed numbers, the chemical potentials, and the entropy will be some function of only the charges. So the idea is to look for the minima of this free energy and then try to extract the different phases. Yes. You will need to, well, I'm not very, oh shit. Sorry, my hearing is not very good and...
So the question is, when you consider these n charges, do you assume that they form a closed algebra as with respect to Poisson brackets, or just any conserved charges are okay in this construction? Higher spin.
I mean, by this construction, the charges will form a closed algebra.
Yeah, that is the question.
Yes, yes,
oh,
yes.
Okay, thanks.
Yes, they will do. Okay, so my table of contents will be a quick look at the SL and R Chern-Simons theory and how these extra charges arise. Then looking at some comments about the spectrum of solutions for these theories, and then looking at the phases, and then what we'll see is that so first we'll have to find the solutions, as an interesting set of solutions. Then we will look at the partition function for this problem, and then look at the different phases for given values of the chemical potentials. And then we will see first that there are Hawking-Page transitions, so there are values of the chemical potentials where the solution or the system will prefer to be on the ground state and not on the black hole solutions. So that will be a situation where the Hawking-Page will act with the Hawking-Page transitions, but also it's a rich set of transitions because there could be transition between black holes. So that means that I have some given values of the chemical potentials, and then I have a black hole, and I move these chemical potentials smoothly, very slowly, and if I cross a given boundary, I cross it, then this black hole will go into another black hole with completely different properties. So that we will call a transition between black holes. This is something you don't see in Schwarzschild ADS, for example. So this is very similar. I mean, the mathematics is exactly the same as the van der Waals-like fluid. Of course, the formulas are very different, but the pictures at the end are exactly the same. So it's like going from the gas phase into a liquid phase. It's a very similar situation. And also there's a second-order transition where you will see this critical line connecting different black holes, and then you move in the other direction, and eventually this critical line disappears, and there's a critical point. So this is basically what I will be talking about. As you see, this is very old stuff in a way. This conference is recent developments in ADS3 CFT2, but this is actually a very old application of statistical mechanics. So this is my only slide on Chern-Simons, SLN Chern-Simons, and the gravitational interpretation. So the idea is that you start with two SL and R Chern-Simons fields. You need two of them. I will call them A and B. In the literature, you will see that one is called A and the other one is A bar, and then when you have complex field, there's a bar and a bar, and then it becomes very complicated in notation. So I prefer A and B. It's a bit simpler. So I have two Chern-Simons fields, A and B. They live on the SL and R algebra, and the equation of motion for both of them are the same, just the Chern-Simons equation. And the trick is that if you define a field that I will call E at the difference of both, and then W the sum, of course, this is an invertible transformation, and then from out of E, I can build this trace of EE, trace of EEE, E4E, etc., up to NE. If I have chosen already my n, so this will stop at n. If you compute the next one, will give you 0. So that means that, in particular, if you have n equal 2, then the only one you can define is this one. But if you have a bigger n, then you can define all these objects. They're all symmetric. And the beautiful statement is that if A and B satisfy these two equations, then all of these will satisfy Frontal highest spin field equations when linearized. This is 2 + 1 dimensions on ADS background. So this has been, well, it's a development. There's a lot of, I was not very careful citing that. I should have included here the literature. There's a lot of literature in this problem. So from my point of view, what I will do is that this gives me a theory of n-1 highest spin fields interacting. This is the interesting point. This is the interacting, and the equation of motions are extremely simple. This is just 2 Chern-Simons field equations. So this theory, first of all, has an asymptotic Wn conformal algebra. There's some references here. Good. This was done simultaneously by 2 groups. This is, you can analyze the asymptotic algebra, and then you discover this Wn algebra. Their solutions carrying all charges, so there are charges associated to this algebra, and then you can build explicitly solutions carrying these charges. It's not quite clear what black hole should look like, so that means that it's not very clear to define the global structure of black hole. Of course, you can find something that will look like a Schwarzschild black hole, but it's very tricky. It's extremely tricky. A black hole is not really something that looks like Schwarzschild. The global definition of black hole is a far more complicated object, and in the case of these higher spin charges, higher spin theories, the main problem really is the symmetries involved. Now you don't have only diffeomorphism, but you have a much bigger group, and you want to define the horizon, for example, in a way which is invariant under, not only under diffeomorphism, but under a much bigger group, and that's something, to my understanding, maybe somebody have mentioned something before, but this is not well understood. Funnily enough, even if you don't understand very well the global properties of black hole, you can compute the entropy, for example, at least for something that you can say, well, this will be my black hole. At least there's a partition function I can compute that is an entropy and a temperature well defined. Okay, so let me consider 2 classes of solutions. This is the simplest you can do. First of all, the problem is understanding a gauge field with 0 curvature. So this is the problem. This is a diffeomorphism invariant theory. It has a 0 Hamiltonian. The time evolution is trivial. The time evolution should not give you important information. Once you have decided the initial conditions, and the initial condition, of course, must satisfy the constraints, then the time evolution is just a choice of gauge. So in principle, AT, I don't have to worry that much about it unless I do something silly. But if I carefully choose a good AT, then time evolution should not be part of the problem. Second, the radial component will be a gauge choice. Actually, these 2 things, of course, are related, but a good gauge choice, for example, would be AR equal to 0. It's just a gauge condition, and it's a good one. And A5 is really what carries all the physics. So you have, I'm working here in a manifold. Let's say at the beginning it could be just R3 or R3 minus a tube. And the main point is that A5 will carry the important information. So the 2 possible topologies, of course, there are many others. You can put 2 holes, 3 holes. That makes it much more complicated. It's one of my future projects, but I don't really know how to deal with it in a clever way yet. So the main the solutions that we will consider, one is ADS phase, which is this is the initial condition. This is the spatial topology. So at t equals 0, this is the spatial topology, and I will say that this is just R2 and nothing else. So if this is R2, then A5 this will be my angular coordinate. It's constrained by this condition. So this must have a trivial holonomy. So that leaves only one state, which is the ground state. On the other hand, the other interesting topology is R2 minus a hole, so this is an annulus, and in that case a phi is not constrained, so because there's a holonomy that I can draw around the hole, and it can have any value. So there's a family of what we call excited states, and they will be classified by the Casimirs of a phi. So this will all come out in a very natural way from the action. That the fact that it's only this what matters, and not a phi as a matrix, but only the Casimirs is what really matters. And this will be the charges entering in the partition function, and they form a closed algebra. These are these objects. Okay, so sorry. Sorry, you're right. No, yes, you're right. Yes, sorry, I was thinking in the... Because these are the Casimirs. Yes. Yeah, by definition. Yes. One second, I was thinking the chart that happened eventually. Okay, so the problem we have is this is the partition function, so we have the Chern-Simons action. Again, we have to go through regularization, quantum terms, and regularization. It's a long story. This is took a while really to understand in the SLN case. It was a bit more subtle than the SL2 case. I mean, at the end of the day, it can be done in the same way. Once it is a sort of calculation that way you understand it, then it becomes easy. But before you understand it, it's very complicated. But then you can prove, I will not do it. If somebody is interested, we can discuss the details. But this is, you start from this partition function, then you go through this typical holographic renormalization, if you want to call it, procedure, and then you end up with this partition function. We have this structure. So here we have n-1 chemical potential, which are fixed, and then they are multiplied by the charges of these Casimir functions, and the entropy. This is it comes out of the calculation. So this is, as I said, this is not something just right. It comes from here. It's a derivation, and the entropy is. So if you remember, there were two matrices. The matrices, the A phi and AT. So A phi, sorry, the charges are defined by A phi, and the entropy is a trace of AT times A phi. Now, what is interesting is that this partition function is really independent of the Chern-Simons detail. I mean, it's something that you can, just from a pure mathematical point of view, would be an interesting object to compute. In fact, it's very similar. A very similar object appears in liquid crystal calculations. We found just by coincidence that it's exactly this object is computed in this liquid crystal system. So you say, let's forget about everything that I've said before. I say, well, let A phi and AT do the computing. SLNR matrices. Let AT be fully constrained by these conditions. And then this is a just well problem where the charges and the entropy are given by this formula. This is a purely mathematical problem that anyone can understand. Let's compute this structure. Of course, the integration of black holes is interesting, and in particular with respect to the spectrum, because for this object to be finite, well, we need again some ranges for these charges. The charges cover values either not bounded from below, say, this object will not be able to find that. This is you will integrate, so you don't integrate all the matrices, but you only integrate all the Casimirs. So A phi is so you summing over all A phi, but what matters, the partition function is only the Casimirs. So you can do unitary transformations there, or similarity transformations that you will not change the conditions of the matrix A, which of course is a measure zero subspace in the whole of possible matrices, when you reach those boundary values, then the chemical